All right, let's get started. Can everyone hear me? Yes? In the back, yes?
Yeah.
Good, okay. My name is obviously not Yisong, I'm Joe. I'm one of Yisong's students. I'm a PhD student here, and I am going to talk to you today about deep learning. It's arguably the hottest area of machine learning, so I'm glad to see it turn out here. So without further ado, let's go for it. So I know, I guess, a little bit about where you're at in the course so far. You've seen linear models, you've seen kind of some basic like decision trees, I think that's true. So in the supervised learning setup, which I guess you're probably familiar with by now, you have some data that you're given. Now this is going to be a certain number of data examples, and each data example might have multiple entries. You could call those features, for instance, and typically you want to associate each example with some label. Now why are we trying to do that? Well, the labels aren't directly observable. There's typically some latent quantity that underlies the data example. For instance, if I give you an image and I want to know what object is in that image, the label is going to be the object class. Now, if your label is continuous, I think you probably have covered that that's typically called regression, and you want to try to fit some function to the values of the output. And if the label is binary, or if it's categorical, if it's a yes or no, or if it's a classification, then we call that classification. Should be pretty standard. Hopefully everyone is familiar with this. So let's go through a little quick example. I think you've already seen this, but if I have a set of data points and I've labeled some of them with class 0, some of them with class 1, and here I have 2 dimensions for each data example, so it's an x1, x2 pair, that's each data example. Well, if I want to fit this with logistic regression, then what I'm going to do is I'm actually going to regress to the logistic transform. And you can think of this as a linear decision boundary. So what determines my decision is a line in this input space. So what is the logistic transform? That's just the log ratio of the probabilities of class 1 to class 0. And so because it's a binary decision here, probability of class 0 is 1 minus probability of class 1. And we're going to fit a line to this logistic transform. And if you rearrange terms, you end up with this form. Hopefully something like this you've already seen so far. And what we'll try to do is we'll just minimize the loss function, which here is the binary cross entropy loss. And we're going to try to find the coefficients of this line. We're going to try to find the slope and like the intercept. And we'll do that through some optimization algorithm, but the common is just gradient descent. So what if I instead have this kind of setup, where now I wouldn't really be able to fit a line to it? Well, if I were to try to find a nonlinear decision boundary, how would I do that? So one option here would be, let's expand out X. Let's expand out our data and give ourselves kind of effectively more dimensions to work with. So by doing that, we can fit lines, or we can fit coefficients to the squared terms here. So we can end up with a hyperbola or a paraboloid in this space. So what I've done is I've expanded x1 and x2 into x1 squared, x2 squared, x1, x2, and then x1 and x2. So this is just kind of a standard basis expansion to give ourselves some quadratic terms. So this is one option, and this will actually work. Another option would be to say, hey, I could actually split this up if I had another line. So if I had another linear decision boundary, I could cut the space up and actually separate out these 2 classes of points. So this is another equally valid way of forming a nonlinear decision boundary. All I have to do is form one line to cut the points in one place, form another line to cut the points in another place, and then I have to decide, based on both of these lines, which class am I in. So we're composing multiple linear decision boundaries in order to form a nonlinear decision boundary. And in both cases, we're trying to get to a space in which the data is linearly separable. That's ultimately what we're after, is linear separability. So let's walk through a short example that kind of illustrates this ability to compose linear decision boundaries. So if I have an AND gate, this is Boolean logic here. If I have an AND gate, then it means I'm only going to say yes if both of my inputs are a yes. Hopefully you're familiar with Boolean logic. Another elementary operation is the OR gate, in which case, unless both of them are no, I'm always going to say yes. And you can see that I can separate both of these sets of points with linear decision boundaries. These are linearly separable. However, if I'm given the exclusive OR, which is I'm only going to say yes if one of my inputs are yes, but not both, I no longer can really separate this with a linear decision boundary, with just one. There's no line that I could draw here that would perfectly separate these two classes of points. It's impossible. However, if I'm given two lines, specifically if I'm given an AND gate and an OR gate, then I can separate these points. I can carve up the space using two lines in order to get this nonlinear decision boundary. So, the entire procedure would look something like this, where first I'm going to take both of my inputs, feed them into an AND gate, feed them into an OR gate. I'm going to negate the AND gate, and then I'm going to take an AND of both of those outputs. And that's going to give me an XOR. So we've taken these elementary linear decision boundaries, we've composed them in such a way that our output is now this nonlinear boundary where we have now sectioned off the diagonal here. Question?
Can you go over real quick how these represent these Boolean operations?
Yeah. So if I want to say I have two kind of variables that are input into this basic logic gate, and I want to say I only want to say that it's true, the output is true if both of them are true, for instance. So I have kind of like a coincidence detection scenario, for instance, where I say if I have two lights that come in, then I want to say I saw both of them. That means that I need to send on a yes signal elsewhere. And then an OR gate would basically just be, if I see either gate active, then I want to send on a yes. But the exclusive OR is the case in which only one gate can be a yes for me to be able to say yes. If they're both yes or if they're both no, then I'm not going to say, then I'm going to say no. Does that make a little bit more sense? Okay. So we've seen this basic example of composing more complicated decision boundaries out of very simple linear decision boundaries. And so what I think you've mostly seen up until this point are these basic linear decision boundaries. Now, for instance, decision trees can form nonlinear boundaries. However, they're always restricted to putting their boundaries along one of the axes of the data input. So they're fundamentally restricted. Now here, we can form these nonlinear boundaries with potentially a more flexible function building procedure. So just to recap, we are going to need to build nonlinear boundaries in order to fit more complicated data. One method for doing that would be to compose simpler linear decision boundaries. And we can refer to depth as the number of stages of processing. So in the same way that we had multiple stages here that we had to go through in order to get this nonlinear output, this is referring to the depth of the computation here. And by deep learning, what we mean is learning functions that have multiple stages of processing. So building up these functions and then learning each stage of processing in order to get the desired nonlinear output. So you might be asking, wait, but we neglected this procedure where we just expanded input space and then used our old favorite techniques of linear decision boundaries. Well, you can certainly do this. There's nothing really wrong with doing that. However, if we use linear decision boundaries, we can actually show that this is a universal function approximator. So if you build up enough stages of processing, enough units of processing within each stage, you can approximate any function. So you really don't have to actually go to this basis expansion if you want to learn nonlinear decision boundaries. So this leads into this area that is come to be called deep learning. It used to be called neural networks. It's had a lot of names over the years, but it has one very basic element, and that is the artificial neuron. Not to be confused with the neurons that are in your brain, which are far more complicated. But these artificial neurons look something like this. You have a set of input features here, and you have a set of weights leading from each of those input features. You take a summation, a weighted summation of these inputs, and then you pass that through some nonlinear function, and you get some output feature. Now this is loosely based on biological neurons, which have dendrites, which collect signals from presynaptic neurons, so neurons that are giving them signals. You have these dendrites that are taking in these signals with some weight as to how they are accounting for these signals. There's some summation at the cell body, and then you send on some signal that happens to be a nonlinear function of the input. So if I take one neuron here, and I put another neuron there, and another neuron there, and so on and so forth, and I compose all of these neurons in a parallel kind of fashion, well, we call that a layer. So this is a neural network layer. And this is kind of one of the basic building blocks of building up deep networks. So I've taken this layer here and I put another layer after it. So now the outputs of those nonlinear functions, of those nonlinearities, become the inputs of the next layer. And then I do a similar type of processing at this stage, and I can continue this indefinitely if I want to, and we call this a network, a neural network. So that's kind of just getting the terminology out of the way. So how do these things actually work? So here's kind of the math that describes what an artificial neuron is trying to do. So you have a summation, let's call it S, and that is the weighted summation of all of your inputs. So this W0 here is representing the bias term. Sometimes you'll see that also referred to as a B. And then you have an individual weight per input for this neuron. And you can vectorize this as just a dot product here of a weight vector dot producted with the input vector x. So I'm referring to that with these boldface W and x here. And can anybody tell me why we have a 1 under the input features?
The bias.
To account for the bias term. So you notice that x doesn't really have an extra term to account for this bias term. So if we wanted to do a dot product, we would have to append a 1 or some other number to x in order to have the dimensionality of w, which I've included the bias term in here, and x agree. Does everyone follow that we need to append on a 1 here in order to have the dot product actually work out dimensionality-wise? And then what we're going to do is we're going to take a nonlinear function of that summation, and that's going to return us this value, which I'll call h here for the moment. And again, we have load. Okay, we have the sum, we have a bias term, we have a set of weights that are multiplied against input features, and then we have an output feature, which is a nonlinearity applied to that sum. And I'll get to what that nonlinearity is in a moment. So I like to kind of visualize these in terms of vector matrix operations. So what we have is just a vector dot producted with another vector. You get a single output. And then what we're going to do is apply a function to that summation in order to get an output feature. So now if we go to the layered level, what is a layer doing? Well, each neuron, each artificial neuron is computing this dot product of a weight vector dot producted with an input vector. Now what we can do is actually parallelize that and have, instead of a weight vector, we can have a weight matrix. So this weight matrix contains all of the weight vectors for all of the neurons in that layer. And so now we get a vector of outputs for our sums, and we then apply the nonlinearity element-wise to each element of that vector to get a new vector out. Again, in matrix vector kind of diagrams, this is one vector that's coming out, and that is the result of a matrix of weight vectors multiplied against one input vector. And then we're going to apply the nonlinearity to the entire vector to get an output. So hopefully that visualization is clear. Now we get to the point of the network. So what we're going to do, instead of having h be the output, we're going to have this new thing, x superscript parenthesis 1, be the output of the first layer. So we're just going to define this for convention to make notation a little bit easier. So we're going to call the input x superscript 0, first layer x superscript 1, and so on and so forth through the network. And now what we do is we, again, apply these operations at each layer, and we go through each layer of the network, computing this matrix times input vector to get a sum vector, then apply the nonlinearity element-wise to that sum vector to get the output vector of that layer. Again, visualizing it, we have this input vector here. We multiply it against the first set of weights, apply a nonlinearity, multiply it against the second set of weights, apply a nonlinearity. We go through the entire network until we get to an output, which can be a vector, which can be an individual scalar number, or can be any other, I guess it has to be one of those two in this situation, but you'll see that it can be much more general than that. And the immediate thing that you notice is that this is actually just one big function. That's all that a deep network is one gigantic function. And the thing that makes this function special is that it has these learnable parameters embedded in the function at multiple stages. And we can learn these parameters. And again, as I alluded to, building up functions in this way, we can actually approximate any function. So just to recapitulate, we have now a method for building up these expressive nonlinear functions with these elementary linear operations and then nonlinearity applied. And it's just an expressive function which actually turns out to be a universal function approximator. And this was proved a number of years ago. So we can approximate any function if we wanted to. And now I want to give more of a geometric interpretation of what's actually going on inside this network. It's easy to look at the mess of arrows and circles and kind of get lost in what's actually going on here. So if we interpret the dot product as actually the shortest distance between a point and a plane, then each artificial neuron defines a hyperplane. So we have this plane in this multidimensional space, and we have this input vector which we consider a point in that space. So what we're actually doing here is we're taking this weight plane and computing with this dot product a distance to the input vector. And so that's what calculating the sum is corresponding to. And now what we do with the nonlinearity is we're actually transforming this distance measure. And this effectively creates a field that changes nonlinearity with the distance from that plane. So if we think of the distance as being represented by this diagram down here, then we find this distance here, we calculate out what that distance is, and then we apply the nonlinearity, which effectively scales that distance in some way. And this is one example of how you could think of transforming the distance. So, given this interpretation, we can actually think of a weight vector as something like a filter, in that it is selective for certain inputs. So if we have a weight plane here, and a cluster of points, often some subregion or some region of the space, and they all have some type of distance, some scale of distance from this plane, then we can think of this weight plane as actually selecting out the abstract feature that is shared by these points. There's some commonality of these points that they're all in this region of this space, and we've effectively cut the space and selected out those points. So you can think of like having this input space where we just cut it up with a bunch of planes, and then those transformed distances give us this new space, which we again cut up with a bunch of planes, until eventually we get to a point at which, if we're doing classification, we want to cut the space with one plane. Here we're doing binary classification. We could do multi-class classification or something more complicated. But this is kind of the general way you can think of it in terms of these geometric kind of interpretations of cutting up the space as we go through the network. So again, we're cutting up the space and transforming it into a new space. That's all we're doing with each layer of processing. So we now need to talk about how we're actually going to train this function. I've given you the general form of the function, but we don't know how we would actually get the function to be what we would want it to be. So it's a universal function approximator, but we need to find the function that we're trying to approximate. So if we think of kind of this hypothesis space of all of the functions we could potentially learn and fit with a given neural network, well, there might be one or might be multiple optimal approximating functions within this space. And we want to find this little dot here when we're somewhere in this space. And what we're going to do is adjust the weights in order to get to that point. And the general paradigm of learning is generally phrased as an optimization problem. I think that's mostly what you've seen up until this point, where what we're trying to do is we have some loss function that we're trying to minimize, and by doing that, we're minimizing with respect to the weights. We're moving around in the weight space to find a better and better function that minimizes this loss. And in order to do this optimization, we need the derivative of the loss with respect to the weight. So this effectively tells us how should the weight be updated in order to decrease the loss. This is just very general for machine learning. And you would typically use some type of update like this, where you're going to take your weight and subtract off a small step in the direction against the gradient, or against the derivative here. And in multiple dimensions, we refer to that as a gradient. You noted with this upside down triangle. So for backpropagation, that's just a method of doing this optimization. So a neural network, again, defines a function which is composed of these elementary operations. And the loss superscript, or script L here, is a function of this network output. So if we want to figure out how to change the internal weights, we can use the chain rule of differentiation to calculate these gradients. So let's run through a very quick example. I'm sure you're all very familiar with chain rule, but for those of you that it's been a little while, if I have some function y here that is a function of two sets of weights, W1 and W2, and I want to find out what is the derivative of y with respect to W1 and what is the derivative of y with respect to W2, what I can do is I can define these kind of intermediate functions here. So if I define v to be this exponent of w1 times x, and if I define u to be w1 times x, then I can rewrite y in terms of just w2 times v, and I can rewrite v in terms of e to the u. And of course, taking the derivative with respect to w2 is fairly straightforward because it's just a linear relationship there. So that ends up being e to the w1x. However, if we want to find the derivative with respect to w1, which is, you can see, is kind of embedded in this function, we can take the chain rule to re-express a derivative of y with respect to w1 as y with respect to v, v with respect to u, and then u with respect to w1. And if we multiply these out, then that gives us the form of this derivative. So it's a way of essentially taking some composed function and breaking it up, and then taking the derivatives of each part as we go back. So this ability to do this here is the chain rule. So let's recall the form of our function. We had multiple stages of layers here, where each layer is a linear decision boundary, and then a nonlinearity applied to that. And we want to calculate these internal gradients, these gradients of these internal weights. So let's start by just looking at the last layer. So in order to actually do this, I'd like to try to kind of draw a computational dependency graph. So here I can think of taking in x capital L minus 1 and combining it, multiplying it against WL, and then I get the sum at layer L, and then I apply this nonlinearity, and then that gets me to x at layer L. And then my loss, if I'm in the supervised setting, is going to be just comparing against some target that I have. So I want the output of this function to match the target as close as possible. And if I want to get back to W capital L, then I'm going to have to traverse through the dependencies in this graph back from L, from script L here, from my loss, to X capital L, to S capital L, and then to WL. Does everyone see how we have to flow backward through the graph to get back to W? Yes. So if we actually wanted to express what this gradient actually is, we can kind of write out in terms of chain rule how we would get back to it. So again, we follow this chain of dependencies backward from the loss, and then that gets us back to W, the weight that we're trying to take the gradient with respect to. And note that here I'm writing this gradient as a kind of fraction partial derivative, just for notational convention. But you see that this derivative of the loss with respect to the output, well, that depends on what form your loss function is. So we won't get into that. Now, this derivative of x with respect to the sum, that depends on your nonlinearity. So that's the derivative of your nonlinearity with respect to its input. And then finally, this derivative of the sum with respect to the weights, that is going to actually just be the activation, the x here at that level, so xl minus 1. And you have to work through kind of this matrix calculus, but eventually you can get back to something that a matrix of derivatives for this weight matrix. And I would highly encourage you, if any of this seems confusing, to kind of sit down with the equations and try to work out how to do these derivatives, because it really helps to kind of build your understanding of how these models actually work. So let's go back one more layer of the network just to see an example here. So let's again draw the dependency graph, where now we're going back to WL minus 1. And we have to again traverse through this entire graph. And this is, again, what chain rule looks like for this graph here, where we've taken the derivative of each individual component as we traverse backward through the graph. So I don't know if you can see it directly, but there are some terms that are reused in both of these procedures. As we're traversing backward through this computational graph, you see that the first two terms here are shared. The derivative of the loss with respect to the output, and the derivative of the output with respect to the sum at the final layer. Those appear in both of these traversals. So what we can do is actually reuse these terms. Specifically, we can reuse the loss with respect to the sum at the layer after, in order to calculate the gradient at that layer. So again, if I have already traversed back to WL here, I've already effectively calculated the derivative with respect to S capital L. So I've already calculated that. I can just store that value And then now when I'm trying to go back to WL minus 1, I can just pick up from SL and then just continue on my way. I don't have to recalculate these gradients as I go backward. So it's a recursive backward computation through the graph. Is that okay? So this gives us the backpropagation algorithm, where let's calculate the derivative with respect to the final set of weights. We're going to store the derivative of the loss with respect to the final summation. And now I'm going to just traverse backward through all of the layers in the network. And I'm going to use the derivative of the loss with respect to the summation to calculate the derivative with respect to the weights at my current layer. And then I'm going to store that summation, the derivative of the loss with respect to that summation that I now have calculated as I've gone backward. And then at the very end, I'm going to just return all of these derivatives. So backpropagation is purely just chain rule applied to neural networks, and you use it to calculate gradients. That's all it is. So just to reiterate, we're trying to do gradient descent, but we need to actually figure out what is the derivative with respect to weights at internal layers in the network. Backpropagation gives us a way of doing what some people refer to as credit assignment. So it effectively says, if I change this internal weight, how is that going to change my output? So I can assign credit from my loss to internal layers in the network. And we see that gradients get backpropagated through the network. And even though I've presented this, you're probably never going to need to actually derive and write out and actually implement a lot of these gradient calculating procedures. Because most deep learning software libraries these days will calculate them for you, which is really, really nice. But also comes with the caveat that if you're not aware of what's actually going on in your network and you're just letting the software handle it for you, it can become somewhat more of a black box. And this automatic differentiation is generally what this is referred to, or autodiff for short. And you can build now any differentiable operation, and you can calculate gradients with respect to internal operations. So now let's get into some of the tips and tricks. So I've presented the vanilla version of deep learning, but there's ways to kind of augment it and build on it. So the first thing I'll talk about is nonlinearities. The nonlinearities are absolutely essential in these networks, absolutely essential. So if we were to just say remove the nonlinearities from the network, this entire function would just collapse. It would turn into a linear function again. So again, if we took this function and just, let's say we removed all of these nonlinear functions, well, if we could just multiply these weight matrices together and get a weight matrix times an input vector. So again, without the nonlinearities, we got nothing. This is just a linear function without them. And so what we'll do is we'll try to build in different nonlinear functions in order to create different kind of output functions. And what are some of these nonlinearities? Talked about them so much. The old school would say, let's use the logistic sigmoid. So this is what you're familiar with logistic regression. This is just the logistic transform. And another option would be, hey, let's use the hyperbolic tangent. Maybe I want my outputs to be something between -1 and 1. But those were the standard for a long time, but the new school, I would call them, are these form of nonlinearities. The main one being the rectified linear unit. So what that is you just take the maximum between your input and 0. So if your input is negative, it's 0 now. If your input was positive, you just return the input. A highly related version is the leaky ReLU, where now you're mapping negative values to some transformed linear function. Another one is a soft plus, which is similar to an exponential. Another one is the exponential linear unit, which is kind of similar to a soft plus. And just at a very broad scope, I hope you can see that there's some very clear differences between these classes of nonlinearities. These top ones up here are what we refer to as saturated. So that means that the derivative goes to 0 at plus infinity and minus infinity. So it's a flat function as we move away. And this new school of nonlinearities, these are non-saturating, meaning that as we go toward positive infinity or negative infinity, the derivative is not 0. Yeah?
Just two quick questions. One on that, is the axis there the product of the prediction and the actual label, or is it just the, okay.
Yeah, so this x-axis along this horizontal axis is saying what is the result of the summation.
Okay.
So that's the sum that's coming in, and then the y-axis, this vertical axis here, is saying this is the output that I'm going to give from my nonlinear function.
And then why have the new school of functions? Because class, like having it be y is 0, 1, or y is negative 1 or 1 seems to fit with the classification method, so why have non-saturating functions?
Yeah. So the main thing I would say is that these nonlinear functions you don't have to use all the same functions. So for output classification, if you wanted to do binary classification, go ahead and use a sigmoid. That's going to map your outputs to 0 and 1. But these nonlinear functions, when they're in the internal workings of the network, have some very strange properties. And one of those properties is what's called vanishing gradients. So these saturating nonlinearities have very small derivatives as you move away from the internal or from the origin. So if we have these small derivatives and we're backpropagating back through the network, then what we're going to end up with is our gradient going towards 0. This is something that stumped people for a very long time. And it seems almost obvious because remember when I said backpropagation involves a derivative of the nonlinearity, and then you multiply all those terms together. People didn't really realize that their gradients were going towards 0 and making it really difficult to train these networks. So again, if we have a product of a bunch of really small terms, our gradients are going to vanish. They're going to go towards 0. And this makes it difficult to train deep networks. That's why people typically focused on just having one hidden layer between their input and output, or maybe 2. So the whole game changed when people started using these rectified linear units. Now your derivative is 1 if you're greater than 0, and it's 0 if you're less than 0. So we're not saturating anymore. But again, if we look at this, we might think initially like, actually, what we still have is 0 here. Why would we want that? This could result in a bunch of what are typically referred to as dead units. So once you send something to 0, it's impossible to get it back from 0 because now you're always multiplying against 0 unless you have some noise in there that you're adding in. But actually, in practice, this problem of dead units doesn't actually turn out to be such a problem. And what we see is that these networks actually do work better than saturating nonlinearities for learning deeper networks. So that was one of the big pushes that kind of spurred a lot of the recent successes of deep learning, was these non-saturating nonlinearities. Now you might also be just saying like, well, okay, so let's try to stay away from these saturated regions. Let's like keep the internal activations of the network away from those regions. So one thing we might say is, well, could we just like stay within this dynamic range of the saturating nonlinearity? And another thing you might be thinking is that these weights are changing during training. So the internal weights are going to be changing. That's going to result in different outputs at internal layers. And now imagine if you're a layer in a neural network and you're trying to learn from your inputs, but your inputs are changing while you're learning. That makes it all the more difficult. So what if you could keep your inputs in kind of a dynamic range, in a nice closed range that you can work with? And this term is called internal covariate shift. It's kind of a jargon term, but if you wanted to know, that's what it's called. So the idea would be, this is demonstrating what could happen. This is my rendering of what it could be. So during training, your output distribution of your layer is going to be changing. So maybe we want to try to minimize that as much as possible. And one method for doing that is normalization. So we're going to try to transform the distribution of activations into a standard normal distribution. Kind of a very basic operation. So we're going to shift and scale our data essentially. Or shift and scale our activations within a network. And there's many examples where people have applied normalization to deep networks, and they typically help quite a bit. This is a very key elementary operation that's useful to use. One particularly useful one is what's called batch normalization, in which we're going to actually keep the activations normalized according to the batch of data that we're using. So we're processing data not in like the full gradient descent setting, but in a batch setting. So what we're going to do is take our summations, we're going to subtract off the mean of those summations calculated from this batch that we're using, and then we're going to divide by the standard deviation, again, calculated from this batch that we're using. And then there's another set of affine transformation parameters. Just if we had to get away from having a zero mean output, we could, in theory, transform this representation. So again, these are batch statistics, and these are additional parameters. Just think of it as an affine transformation. So we're going to keep the activations in a similar range. This is going to help to speed up training, which in effect it actually does. And it also has another effect, which is that it adds stochasticity to these activations. It adds stochasticity to the network. There's a bit of randomness depending on what batch you actually selected. And so that stochasticity actually has a regularizing effect. Question?
When you talk about internal activations, are you talking about the output of the linear transformation or the nonlinear?
Sort of both. Typically people use, well, I've actually seen people use activations to refer to S or to X. But here I'm kind of just saying, in general, we want to keep these activations in a range. It could be either one. But here we're normalizing the summation specifically. So as I just mentioned, regularization is a huge thing. I think you've talked a little bit about maybe L2 weight decay or things related to that. But these networks are amazingly flexible. There's been recent experiments that have shown that these networks are perfectly happy to fit random noise. They will do it with ease. And so what we need to do is regularize the network somehow, typically. And what this actually means is formalizing some prior beliefs that we have to kind of constrain the possible solutions that this network can find. So these are prior beliefs either on the model or on the data. And these, I tend to think of these in two flavors. One of them is this stochasticity, which I mentioned, which you can think of as kind of adding some level of uncertainty to various parts of the model or the data. So one thing that we just mentioned was batch normalization, in which we have some stochasticity based on the batch that the network is running on. Stochastic gradient descent is inherently stochastic, so you're not fitting the entire gradient with respect to the entire data set, but rather just a small batch of the data set, which you believe to be representative of the data. And another very popular one is what's called dropout, which what this actually corresponds to is a Bernoulli prior on the activations of the network. So in effect, what that actually means is that you are randomly going to drop entire units from your layer. So you're going to calculate all the units, but then maybe shut off half of them and then send on just the ones that were active. So we have this like internal switching randomly on and off of these units, which has been kind of shown to help in encouraging the network to really find robust solutions. And so it can't overfit and kind of use all of its weights. It has to find solutions that really force it to generalize a little bit more and find more like independent filters. The other flavor of regularization is I think of as constraints. So one type of constraint is early stopping, in which case you're looking at your validation set, and when your validation loss starts to go back up, then you just say, okay, we're going to kill it right here, or we're going to lower the learning rate, or something like that. But you're always constantly watching the validation set in order to not overfit on the training set. So that's just a very common technique. And then another one is some type of weight decay on your weights. For instance, here I'm showing an L2 weight decay, which says the further that the weight gets from 0, I want to penalize it back towards 0. I have this prior that my weights are going to be small, and I don't want my network just changing its weights around in any old fashion in order to fit the function. And it's important, if you haven't already discussed this, that you regularize only the weights and not the bias term, because the bias term is still quite helpful in terms of forming a linear decision pattern. Another very important area to be concerned with is the initialization. So what we're doing is we're starting off a network with a set of weights, which we initialize somehow, and then we optimize to get to some hopefully good solution in the loss space. And if we initialize the network in a bad region of this weight space, well, it could actually cause the network to just blow up or not learn at all. You can think of, if you had your network just have weights of all zeros, then actually what you would end up with is gradients that are all zeros. So the solution of having all zeros for weights and biases results in a local optimum, which obviously it's hard to get away from that. So some common strategies that people use are they'll initialize the weights from some uniform distribution within some range around 0, or from a Gaussian distribution with some width. And how you determine what size these distributions should be depends on the size of the layer. So there's some strategies out there in order to, if you think of having a really deep network, if you had big weights, your activations would just blow up the further you got through the network, probably. So there's some strategies out there for how you actually pick the size of these distributions that you're drawing from. And then another important topic is optimization. You could spend a lot more time talking about it, but typically what people start with is stochastic gradient descent. But there have been a lot of new methods recently that have tried to incorporate additional terms from the gradient, like decaying moments of your previous gradients. So you take like the average of all your past gradients and use that to help keep you going in whatever direction you are already heading in. And there's also strategies for scaling the gradient based on each individual parameter, so that maybe you want to update some parameters more than others. So I'll just show you that this is a variety of different optimizers. What people started to use about maybe 5 years ago was this thing called momentum, which just says I'm going to maintain my previous gradient and follow that in a little bit, or I'm going to follow that with some direction as well. And then recently there have been a lot more developments like AdaGrad, AdaDelta, RMS Prop. These are all just fancy optimizers that take a little bit of extra information into account in order to hopefully get to better solutions faster. There's really not very much theoretical understanding of these optimizers. It's very hard to prove things for anything other than stochastic gradient descent, but empirically they do tend to work quite well. The default for most people these days is this optimizer called ADAM, A-D-A-M. So, and You might be worried that maybe we'll end up in some local minima or a saddle point here. And in practice, that actually doesn't seem to be such an issue as long as you're regularizing properly. Because when you have more dimensions, that actually gives you more dimensions in which you can move in. So the probability of you being in a local optimum in every single dimension actually decreases. And you end up in a set of, there's effectively very many local optima, but they're all effectively equally good. At least that's the conventional wisdom at this point. Finally, we've really only discussed this sequential kind of connectivity, where you pass the input into the first layer, then that goes to the second layer, third layer, fourth layer, so forth, all the way until the end of the network. And we see that information actually has to flow through the entire sequence to reach the output. But just purely from like a heuristic point of view, we see that information may not be able to propagate very easily through this network. If we don't know the parameters, we have to propagate through the entire network, and then we have a very weak learning signal. We'd like to maybe be able to have shorter paths through parts of the network. And this actually helps quite a bit in training better, more expressive functions that are easier to optimize. So one kind of way of doing this we could think of would be having the previous layer just be element-wise added to the output of the next layer. So you're constantly adding in the previous input. So you can therefore just send on copies of the previous input. And if we didn't want to send, or if we wanted to send something at an intermediate layer all the way to the end, we could just zero out the weights in all of these, the layers afterward, and just send it on directly. And another method of doing this would be dense connections, which I sometimes refer to as concatenated connections, where you actually have a direct connection between each node and each node after it. So now I can just directly send my input to my output. And there have been a lot of recent work showing that these models are actually much better than these previous kind of sequential connected models. So I wanted to just take a brief moment to talk about how you'd actually implement these things. I think there's going to be a recitation section tonight on Keras, which is a deep learning library. But if you wanted to actually implement one of these things on your own, how would you go about doing it? And I think the main thing is that you need to take advantage of current hardware for doing parallelized processing. So there's two main ways that you can do, or that you can incorporate parallelization into implementing these networks, and that's through the matrix multiplications, and that's through these pointwise operations, such as pointwise nonlinearities, pointwise addition and subtraction, multiplication, division. And so recall that we have this artificial neuron here. And if I wanted to, I could, again, take multiple weight vectors, combine them into a weight matrix, and now I get out a sum vector. So we're parallelizing across the units that we're calculating here. And all of these operations can be done simultaneously because they don't depend on each other. And so we can parallelize our networks in that way. And then another way that we can parallelize the networks is through actually processing batches of examples at the same time. So I think you're probably familiar with this, but you're going to feed in not just one data example, but multiple data examples, potentially the entire data set. But you can run multiple data examples through the network and calculate multiple outputs. And again, because these are separate data examples, their computations don't depend on each other unless you're doing batch norm or something else, and you can calculate these all in parallel. And there's a lot of new software out there for utilizing graphics processing units, GPUs, which are amazing at doing these matrix multiplications and pointwise operations. And I'll talk, I think, a little bit about that later. So if we want to actually put this into code, how we do that? Well, we could define maybe a function for an artificial neuron here, or for a layer actually, and that would just say I'm going to take an input x, and I'm going to have a weight vector w, and I'm going to just dot product those. And if I want to do a ReLU, well, I'm just going to take the maximum of the result of that dot product and 0, and then I'm going to return that. So this is a very, very basic implementation of how you actually implement the layer operations. But actually, I guess the more conventional way to do it would be to actually make this a class in its own right, where now this neural network layer object has its own attributes and its own methods. So what we would have is the neural network layer actually holds on to its own weight matrix, which we are initializing here from uniform of negative 0.25 to 0.25. And then whenever we call this layer, then we call it with some input x, and then we just calculate this dot product send on the output. And more sophisticated implementations will have this class object hold on to its gradients, hold on to previous, previous activations and things like that. So manually implementing backpropagation is a real chore, although I would recommend it. It's a good way to get very familiar with the operations. But if you're in general just building up some arbitrarily large computation graph, you don't want to have to calculate these gradients by hand and then hard code them in the network every single time. It gets really, really tedious. So most libraries, as I said before, will automatically calculate these gradients for you. If you're using Keras, you're never going to need to calculate a derivative. And there's many, many libraries out there. It's really a matter of preference what you use. Keras tends to be one of the easier ones to get started with, although it does have some limitations in what kinds of operations are just easy to implement. So I typically use TensorFlow or PyTorch. Those are my go-tos, but it's really up to you. They all implement a lot of the same basic functionalities. And the nice thing is that all you have to do is just build the computation graph and then define the loss, and then all the gradients come for free. So now I wanted to take a little bit of time to just go through what I would refer to as a buffet of ideas. So there's been a huge number of ideas that have come out of deep learning in the past 5 years or so. And so I don't want to give you the impression that it's all just these nice little linear transform, nonlinearity, linear transform, nonlinearity. There's a lot more complicated and really interesting things you can do with these networks. And one thing that you can do is what's called attention. And what that effectively is a pointwise multiplication that weights the elements in a vector or a representation. So here I have you'd have a set of feature maps from an image, for instance, and you have a recurrent network, which I'm going to talk about on Tuesday, and you can look at different parts or you can weight different parts of the images, or different parts of the image, to generate a caption for what you think the image is of. So you can think of this as if you're looking around, a visual scene and you're trying to describe it, you wouldn't want to just kind of look at the entire thing and describe it. You might want to focus on little details as you go through. And this pointwise multiplication here is what's called soft attention. So you can, because it's a multiplication, you can differentiate through that. You can say, how should I have improved my attentional weighting? And this is opposed to what's called hard attention, where you actually do a specific sample of, I'm only going to select out part of the image, for instance, in this example. And this is more difficult to train because now this is a non-differentiable operation where you need to figure out how you should have selected a patch of the image, but how do you tell it, hey, you shouldn't have selected over there, you should have selected over here, then you would have gotten the answer. It's more difficult to do that. So there's this problem that we see where a lot of sampling operations are actually non-differentiable. Because once you've sampled something, that's like something you can't necessarily just undo. And standard backpropagation isn't going to work for that, because you have an infinite gradient where it changes from the value that you sampled, and then zero gradient everywhere else. So that's something you can't use for backpropagation.
Excuse me. What do you mean by sampling operations?
Yeah, so what I mean by sampling is, say I give you the choice, hey, do you want vanilla ice cream or chocolate ice cream? And you say chocolate ice cream. Now, I can't differentiate through that decision because it's now a hard decision of, hey, now it's just chocolate. So in the same way, you can sample from, so that would be like sampling from Bernoulli distribution, or I guess not quite, but you can sample from Gaussian distributions, multinomial distributions, things like that. Yep.
So with convolutional networks, you have pooling layers, which are effectively a sampling operation. How do you deal with that?
Yeah, so in a pooling layer, you're actually only backpropagating gradient through to the value that was selected out of pooling. So you can backpropagate through that operation, but for instance, the pooling method, for those of you that are not aware, like pooling is this operation where, so in max pooling, you just take a window of values and select out the maximum value from it and say, this is what my value I'm going to send on is. But that operation, that pooling operation is totally hard-coded because I'm just taking a maximum. I'm not learning which value to select. If I were trying to learn how to select the value, then that would be non-differential. So one method of getting around this would be, say if I had a continuous distribution like a Gaussian here, instead of sampling from a Gaussian, I can actually reparameterize this as my sampled value is my mean plus my standard deviation element-wise multiplied against some standard Gaussian noise. So these two methods will give you the exact same distributions of values, but you can actually backpropagate through this second operation because it's fully expressed in terms of just element-wise operations. But the point is that these gradients are now going to be stochastic because I've had to sample a noise value here in order to evaluate the sample. So the gradients I'm going to be passing back through the network are stochastic gradients. They're not deterministic. And there's actually a pretty big literature on this. It's growing quite recently. There's been a lot of introductions. But generally, if you don't have a distribution that you could reparameterize like this, then you're going to be forced to use something like the reinforce algorithm, which is also sometimes referred to as the score function estimator. And there's a bunch of more recent work in this area that has shown how you actually would try to estimate these gradients. And it really boils down to a bias variance kind of decomposition, where you want to have an unbiased estimator of the gradient that has a low variance. And that's essentially what people are trying to come up with. Another area is what I would refer to as learning to optimize. So before we talked about like stochastic gradient descent, oh, there's a question. Sorry. Oh, you did? Oh, you did. Okay. Before I talk about stochastic gradient descent as like an optimization procedure, but actually optimization is itself, you could think of sort of a task that you could train a network to do, where what you're trying to do is update the current estimate. Here I'm calling it theta. I want to estimate a delta theta given that I have theta and a gradient. So if I know the direction of maximal change and I know where I'm at currently, I could, for instance, learn how to actually take a step in this space. Where here, f is the optimizer function, theta are the parameters of the function that we're trying to optimize, and we're going to actually learn to perform optimization. It sounds like a really crazy idea, but it's actually been shown that you can do this, and it outperforms these hard-coded, handcrafted optimizers like stochastic gradient descent, and even Atom, which is kind of the leading optimizer right now. So you can actually learn how to perform this optimization, and it performs quite well in practice, although it remains to be seen whether it's truly scalable. Yeah.
So I'm not sure I entirely understand which part of the process it's learning, because it's taking the gradient as an input.
Yep.
So if it's like if you're training it to optimize like some like linear polynomial regression problem, isn't it just going to subtract the gradient times the step? What is it learning?
Yeah, so think of like stochastic gradient descent as a something like a linear model, where your input is your gradient, and then you have some alpha parameter, your step size, like you said. So usually what you do in practice is actually hand choose what that learning rate is going to be. And usually you'd set it as the same learning rate for every single parameter. But in practice, a model could learn how to change that learning rate per parameter and learn how to make very large jumps and just ignore parts of the gradient when it's very, very far away from optimal values. So if I'm very far away in parameter space and the model kind of has an idea of, oh, okay, this is not where I think an optimum is going to be, I can take a large step that I wouldn't be able to do with a normal optimizer. So you're kind of learning these learning rates. Yeah?
With this kind of setup, would you have to, I guess, relearn an optimizer for any given optimization task?
It's interesting because you actually don't. There's a paper, so at the bottom here, there's a paper by Andrejkowicz et al. 2016, where they showed that you could train an optimizer to optimize the parameters of a network for learning how to do, for learning how to classify MNIST, which is this handwritten digit data set, and then you can take that optimizer, well, I guess you could, I think in the experiments that they showed you, you could train an optimizer to optimize specifically for training on some classes of images, for instance, and then apply that optimizer directly to a model that's trying to learn other classes of images. And you can actually change the network architecture and it'll still perform the optimization for you. Another really interesting area is what's called adversarial examples. And it's kind of this weird thing where you can take a data example and actually manipulate the data example itself using backpropagation and have it go as far away from the correct output as possible. And you would hope that, for instance, if I give you an image of a dog and I say, manipulate this image so that you don't think it's a dog anymore, it wouldn't look like a dog eventually. But if you actually run this procedure, the images don't change qualitatively, but they are incorrectly classified. So what you can take is a network that would classify this image as a panda, for instance, and then add some adversarial noise. So you're specifically pushing the image away from what the network is supposed to say. And even though the image still looks qualitatively the same, the network actually is highly confident that this is something totally different. And this actually can be done in the real world too, because these adversarial examples, for whatever reason, happen to actually generalize across different networks. So you can actually change stop signs and have them, to a computer vision algorithm, look like something that's not a stop sign. Which a lot of people are worried that this is going to totally mess up self-driving cars, but I think it's not such an issue, and hopefully we'll figure it out soon. Another exciting idea is Bayesian neural networks. So up to this point, we've just been calculating a specific value, but what if we had some uncertainty on our weights, or what if we had some uncertainty in the activations of our network, and had actually distributions for each of these values? Then we might be able to, instead of having a new example and saying whatever output the network says, we might be able to say, hey, I think it's this, but actually there's a lot of uncertainty in this parameter, or in this output value. So what we're actually doing is placing prior probabilities on these qualities, and this can help to prevent overfitting to low data regions. Generalization is also an interesting topic. As I said, you can fit random noise with these networks. And this goes against a lot of the conventional wisdom that what these networks are learning are like this abstract hierarchy of features, but it turns out that doesn't seem to be totally the case. But there is different behavior between fitting noise and data. So what I'm showing here is a plot from a recent paper where they took kind of one of the state-of-the-art models, and what they did was they just fed in the same data examples, but they randomly permuted the output labels that they wanted the network to fit to, And you see that this red curve here eventually reaches a loss of 0. So it is able to fit perfectly random labels. What's more, you can actually shuffle the pixels, and this is a convolutional neural network where that shouldn't be able to work, and it still will fit it with 0 loss. You can even have random pixels. You can have absolutely random noise that's going into the network, and the network will still learn to fit it. So this is quite scary, because this kind of says that we have this maybe overly expressive function. How are we sure that it's actually learning something that's reasonable and not just totally overfitting it? But you can see that there are different behaviors for training on true labels versus random labels and random data. But it is something to kind of keep in your back pocket and know about. And finally, I want to talk about really a more theoretical approach to understanding what these networks are doing. Up to this point, it's been mostly like an experimental kind of, or an empirical kind of explanation of what a deep network is, but I haven't really told you what they theoretically do. And I would say that the leading theory out there is this information bottleneck theory. And what that says is that what we're trying to do with the deep network is maximize the mutual information in the information theoretic sense between the input and output while discarding all other input information. So we're trying to take our input, which has all of the information necessary to predict the output, and we're trying to effectively just compress out those useful bits of information. And this is kind of the theory of what deep networks are able to do, which is they learn these representations that compress the input while preserving just the relevant bits for this output. And there's these nice diagrams here where you can see that at the beginning of training, so that's this very bottom level here, you have the first layer of the network contains all the information about the data and all of the information about the label. So that's just, by default, it's always going to have that amount of information. And now the second layer slowly starts to get more and more information. It gets a little bit more information about the label while kind of losing some information about the data. The third layer, in this kind of pinkish color, does the same. It slowly gets more and more information about the label, and then you can see as it goes toward the left, it starts to lose information about the input. And finally, you see like these last two layers are just totally trying to get more information about the label and discard information about the input. So this is at least one theory that's out there, and it remains to be seen whether this can really be validated in more complicated networks. It's difficult to really do these analyses, but it's an exciting idea and hopefully one that leads to more insights. So I want to take a little bit of time to discuss some perspectives. So this is where I take off the lecturer hat and kind of give my own 2 cents. So I want to just discuss kind of the history surrounding deep learning. So this idea of like training machines on data goes back to like really even before the invention of the computer, but you can definitely see in Alan Turing that he was thinking about this, where he said, you know, wouldn't it be better to actually simulate a child's mind and then teach that child, rather than trying to simulate a model that just knows everything already? So you can see, like, having a model, training it on examples, it's basic machine learning right there. So back in 1943, there was these 2 guys, McCulloch and Pitts, that introduced this thresholded logic unit that was kind of the basic precursor to artificial neurons. This was their idea of, you know, this is maybe what a neuron could be doing at its most basic operation. And then in 1957, Frank Rosenblatt introduced the perceptron learning algorithm. There was a lot of excitement around this because you could train these models to recognize very basic shapes and digits and things like that. And it was an exciting time. And there was a lot of hype that built up around the perceptron And people got so excited and said, oh, we're going to solve artificial intelligence in 5 years, it'll all be done, don't even worry about it. But then in 1969, things didn't quite pan out, and then Minsky and Pepper showed that the perceptron is actually unable to learn the exclusive OR function, which we talked about. So this linear model is not able to do this basic XOR function. How can we ever hope to learn anything more complicated? And basically all research stopped on neural networks for quite a while. And this is what's generally referred to as the first AI winter. And then in 1982, things started to kind of pick up, and John Hopfield here at Caltech introduced the Hopfield network, which has a set of auto-associative memory states. This was a pretty exciting thing at the time. In 1985, Hinton and Sinofsky introduced a method for training restricted Boltzmann machines, which is an unsupervised learning algorithm for generating data. And then in 1986, the backpropagation algorithm was introduced, although it's interesting to note that the algorithm was actually introduced as early as the 1960s, but people just didn't really catch on at that point. So in 1986, people showed this, and it was quite an interesting time. People were starting to get more excited about neural networks again. Maybe we can actually train nonlinear functions that can do these XOR operations, but also do a lot more nonlinear processing. In 1989, Jan LeCun introduced convolutional neural networks, although similar ideas had already been around. There was the LSTM in 1995. And I'm going to talk about some of this in the lecture on Tuesday. And then in 1995, there was this new generative model called the Helmholtz machine, which is kind of like an autoencoder in which you're taking the data, encoding it in some way, and then decoding from it. This was also a very exciting model at the time. But overall, the field kind of collapsed into this general disappointment in neural networks because they just didn't seem to scale. For the problems that I was talking about before with these vanishing gradients, the fact that they're very computationally intensive to actually train these models, people tended to move toward support vector machines and toward kernel methods for training these for training their models. And this is what's called the second AI winter. And then it was really in 2006 that there was a new method for training deep restricted Boltzmann machines, which layer-wise, which you can get what's called a deep belief network. Don't worry if you don't recognize all the jargon, but this was a big breakthrough. And then people started to slowly realize actually you could train these models on GPUs, and that would be much, much faster. And there's new ideas about maybe we should use non-saturating nonlinearities, that might work a little bit better. And then really the lid blew off in 2011, 2012, when Geoff Hinton and some of his students completely just dominated one of the most, one of the largest image recognition benchmarks and showed that deep neural networks really can scale to some of these more complicated problems. And since then, it's just been a blossoming of just a million ideas coming out of deep learning. Everything from generative models, so we can generate images now, we can generate speech. There's generative models running on your phone as we speak. There's this entire area of deep reinforcement learning, using deep networks with reinforcement learning to parameterize policies and parameterize value functions. And then there's these super deep networks that get created. Here, there's networks that have 50 or even 150 layers. And so we're really in a golden era of research on neural networks. It remains to be seen whether or not this will actually continue, but for the time being, that's where we are. And I think there's a general sense of hype in the field right now. So in order to address that, I just want to say that deep learning has objectively helped to solve some new tasks. So we can now extract useful information from images that we didn't used to be able to extract, such as what object is in there, where it is, and what pixels exactly. We can process speech, we can process text, and understand aspects of these, or train models to output aspects of these inputs. And we can also train models to perform virtual or physical control tasks. This is definitely a big step forward for robotics. But I guess it's important to maintain this view that there's still many tasks out there that are unsolved. And if you really think about it, like, it's amazing how capable children are. And none of our machines are anywhere as near as capable as a human child. There's just so much left to be done. And a lot of that future success depends on a lot of areas that are not directly under control of researchers. We just need more data, better hardware, more computing, and more theory. So really the theory aspect is only one part of it. And a lot of the successes recently have actually been fueled by more like data and compute rather than theory. The theory was already mostly there for a while. So there's been a lot of times where these breakthroughs, like looking at some of these old drawings, you're like, obviously, like if I was able to give this lecture to somebody way back then, they'd be like, oh my, their mind would be so blown. But it took 70 years to go from these very simple networks all the way to these more complicated networks, and there's a lot of progress that's happened in that time. But things have changed quite a bit, and it's important to remember that, like, as amazing as this stuff is today, it's all going to seem super primitive eventually. There's a lot left out there to be discovered. So, to wrap up, I guess the question now is, like, is deep learning really here to stay? Is this just a fad, or is it going away? And definitely, it appears that depth is a very important aspect for machine learning. Because, and I haven't really shown it here, depth controls the number of parameters. You could learn the same function with a shallower model, but it would require exponentially more parameters. So this depth actually allows you to have some savings in the number of parameters, and it actually allows you to learn these complicated nonlinear models. And a lot of the new tools that are around now, such as GPUs and such as the software libraries that have been introduced, those are very general purpose. They're not specific to deep learning per se. You can do a lot of just very basic mathematical operations on them. So it seems like those will be useful, at least for a while. So I think the field is going to change quite a bit, but I guess the underlying motivations of wanting to learn these expressive functions is going to remain the same. So some aspects of deep learning are definitely here for the long haul. So next time, I'm going to be giving a lecture on Tuesday, and we're going to be talking half the time about convolutional neural networks, and the other half the time will be about recurrent neural networks. Up above, I just want to highlight that this is kind of the state of the art right now for object detection and segmentation. And you see that the individual people, individual bicycles have been segmented out. So a deep neural network has learned how to output a mapping that says this is where this person is, this is where this bicycle is. And you can't really see it exactly, but there's boxes drawn around each person, each bicycle, everything in the image. And all these models generally rely on convolutions, which is a way of kind of restricting a network in some way in order to make learning more tractable. And then down below I'm showing, this is a cell from a long short-term memory network. And these networks have become very, very popular as they're able to hold on to information from a temporal sequence for a longer duration. And these types of models have recently morphed into this thing on the left here, or on your right, the differentiable neural computer, which is a kind of a larger version of this, where you can read and write from a memory bank using a recurrent network. So that's